किसी का कोई सवाल हो? असाइनमेंट कर ली थी?
यस सर।
हो गई
सर वो जो
पोलर कोऑर्डिनेट्स में? चलिए ठीक, थैंक यू। So let me quickly recap some of the main points of the last lecture. If you remember, in the last lecture what we have studied is we have discussed about the analytic or holomorphic function. We said that any function f of z is analytic if it obeys the Cauchy-Riemann conditions. And you remember I said that there are three conditions. Third one, which is most important, was the Cauchy-Riemann condition, and that was on the partial derivatives. So we said that the partial derivatives of the real and imaginary part, basically we have written, let's say, w in terms of u and v, and u and v were the coefficients of x and y. We said that they should have to have the partial derivatives. Their partial derivatives should be continuous. If these two conditions are all there, and Cauchy-Riemann conditions hold, then this function is analytic. And you have seen something that f of z, which is equal to z star, where z star is the complex conjugate of z. It obeys the first two conditions. Du by dx exists, du by dy, dv by dx, and dv by dy. Du by dx, dv by dx, etc., they are continuous also. But the problem is Cauchy-Riemann conditions are not obeyed. That is why I said that f of z, which is equal to z star, is independent of f of z, which is equal to z. So z and z stars are two distinct, you can say, functions, two independent functions. So the quickest way to check the analyticity of a function is take a partial derivative of a function which you wanted to check that if it is analytic or not with respect to z star. And if it is equal to 0, it is analytic, otherwise it is not an analytic function. And you remember that last time what we have studied is we said that, okay, this is the this is a complex plane. I'm considering ordinary complex plane, not extended. Extended complex plane has an infinity, but that's a separate business. And this you can see in this imaginary of z. And I used to call them as x, and this is defined as y. And if you remember, we said that if we have any point z naught, then we can approach to this point from any side, right? I mean, on a y-axis, you can approach delta x is equal to 0 from left side or right side, from this way or this way. Similarly, you can do same with the y. And some of you were bothered that why, how we can prove it generally. So the idea is I have tried to prove it in the form of a polar coordinates. You remember in the polar coordinates, imagine you have a circle, and on that circle you have a z, and from a z you can go to that z plus delta z. Where delta z is, is what? Where delta z is delta x plus iota delta y, right? You can take any value of, let's say, you can take z to be delta z to be small, anything that you can write, for example, a circle of radius a and e to the power iota theta. You can see that no, this is a circle with a radius a, and you can write this as an e to the power iota theta, so that you can calculate delta x is equal to a cosine theta and delta y is a sine theta. So it means for any z, what you have now is z plus a cosine theta and z plus a sine theta. Now if you have any function f, which is basically u plus iota v, you can call it as a function of z. And if you calculate df by dz, what was the definition? The definition was f of z plus delta z minus f of z over delta z, and you can take a limit delta z approaches to 0. Now you see, I can say delta z approaches to 0 if a approaches to 0. It's a small number. Now what you can do is, this is by definition df by dz is, you can write it as du by I say d but write partial x plus du by dy delta y, right? Because this u is a function of, by definition, u was a function of
X and Y.
x and y, and so is the v is a function of x and y. Then you can write plus iota partial v over partial x delta x plus partial v over partial y delta y, and then you can write delta as z as a e to the power iota theta. You can take this e to the power iota theta upstairs. Delta x has an a, delta y has an a. You can take a to be common, this radius is gone. So it doesn't matter if you take delta z goes to 0. So that's why you can say it as du by dx cosine theta plus du by dy sine theta plus iota dv by dx cosine theta plus dv by dy sine theta, and then you have this whole thing is multiplied with kind of a, you can say, phase e to the power iota theta minus phi sine. Yeah, exactly, thank you. Now you remember the Cauchy-Riemann conditions. The Cauchy-Riemann conditions were, let me write them over here. Du by dx is dv by dy, and dv by dx is minus du by dy. Now instead of a dv by dx, you can put minus iota du by dy.
Yes.
Instead of a dv by dy, you can put du over dx. So you can take du by dx to be common from this term and this term, right?
Yes.
And then you can take du by dy to be common from this term and this term. So what you have is, let me write e to the power minus iota theta here, and yet then you have du by dx, and you have
Cos theta.
cosine theta, let me write it as a c theta to save my time, plus iota
Sin theta.
s theta. You can take minus, sorry, this was, there is no minus. This, you can take minus sine, minus iota to be common from this. So then it becomes minus iota du by dy. Then you can see, you can have c theta plus iota s theta. Because if you take minus iota to be common, it has no iota. So it becomes minus 1 over iota, which becomes plus iota when it goes upstairs. So you can see, this is e to the power iota theta. This is e to the power iota theta. So this, and this is gone. So it has no dependence on angle wherever you move on this circle. And this was a circle of a fixed radius, and the direction is dictated by delta theta. That is why I said that this is a better way to prove that. Instead of approaching from x, y, or any other side, you can approach it on a circle, and you can prove that it has no dependence on the angle. No, this is fine. This was your question last time. All right. So there was only one point which was left in the last lecture, and that was the entire function. So let me define what is the entire function. So now we understand what is an analytic function. If a function is analytic in a complex plane for modulus of z less than infinity, then that function is known as an entire function. Entire function has to be analytic function. So this, instead of writing it as an entire analytic function, we just write a small word, entire function. So any function that is analytic for z modulus of z less than infinity is known as an entire function. And you have the example, z is an entire function. Z to the power n is an entire function. But there is a condition. N should be greater than 0. By the way, it is equal to 0, and that is a special kind of an entire function, and this I'll give you an assignment to prove that, okay, the constant is also an entire function. So if you have n greater than 0, it means you have all powers of n which are positive. And you can write exponential function as a series. And what is the series of e to the power z? By the way, do you think e to the power z is an entire function? Sorry, is an analytic function, f of z? Of course, of course. Is equal to 0, sorry. So, of course, it is an entire function. And you can write it in terms of its series, that summation upon n is equal to 0 to infinity. You can say z to the power n over n factorial. If z to the power n is an entire function, then z to the power n over n factorial is also an entire function.
Yes.
If that is an entire function, how about sine hyperbolic, cosine hyperbolic? By the way, just a moment, how about this one? Let me first, e to the power minus z. It is an analytic function. But I can also write it as summation upon n is equal to 0 to infinity, and I can write it as minus 1 to the power n z to the power n. I guess that is correct. All even powers have positive sign, all odd powers of z has negative sign. So I have to multiply with minus 1 to the power n.
यहाँ पे n को 0 से start करेंगे.
Series start from 1.
लेकिन z पर 0 जो है नहीं होना चाहिए ना.
Then if you have z is equal to 0, then you have 1. It is not an exponential series. I have written e to the power z.
नहीं, ये जब सीरीज ओपन की है तो इसमें z पर n है.
ये इसकी सीरीज है ना?
हाँ जी.
If you
यहाँ पे n इस सीरीज में जब हम n 0 पुट करेंगे तो z पर 0 होगा.
no problem, that is a separate function. This is a separate function. F is equal to z, f of z is equal to 1 is an analytic function. But this is an analytic function in an extended complex plane, even if you take z is equal to infinity, because there is no z in it. Such kind of functions, which I want to hide it, and you asked me quite earlier. There is a famous theorem which is known as a Liouville theorem. Liouville theorem says that if you have a function which is analytic on an extended plane, then the only possibility is that it is constant. And this you can prove. I'll give you an assignment to prove it. So you are very right. One is an analytic function, but the beautiful analytic function, because it is analytic not only for ordinary complex plane where z is less, modulus of z is less than infinity, but even in the extended plane, complex plane, right? So it means if these two are analytic function and they are entire function, their combination will also be an entire function. So I can write cosh or cosine hyperbolic as e to the power z plus e to the power minus z over 2. And you can also write sine hyperbolic. By the way, this is the even power series of the exponentials. Sine is the odd, this sine hyperbolic is an odd power series of this one. So this is e to the power z minus e to the power minus z over 2, right? No iota in this one. Similarly, you can prove that cosine hyperbolic, cosine z and sine z are also the entire functions, because then you can write iota z, no problem. You can take iota to the outside, iota to the power n, no problem at all. So how about tangent hyperbolic z? Tangent z, it is sine hyperbolic z over sine hyperbolic over cos. But the problem is cos hyperbolic can be 0. It means it is analytic except at cos hyperbolic is equal to 0. Therefore, we cannot say that it is analytic everywhere on a complex plane. That is a problem. So how to deal with these kind of functions which has a singularity at a point, this we will discuss in today's lecture. By the way, this tangent is a very special kind of a function, and I'm not sure if I find some time to calculate this zeta function, because they have the cotangent hyperbolic function. That is a wonderful applications in condensed matter physics when you do this Bose-Einstein condensation.
Are you thinking of cos, or are you thinking of tangent?
A tangent, because you see that cosh hyperbolic z, this can go to 0 at some angle.
At some angle.
Yeah. And that's not a single angle, that is a multi-valued function. And then we have to define a branch cut, that's a later point. But the problem is whenever you have something that is going to 0 in the denominator, the function has a singularity. And to deal with these kind of a singularity, Anywhere in the complex plane, exactly. Because these are all entire functions. The problem is this was an entire function, this was an entire function, but this ratio is not necessarily an entire function. Does it seem fine? Okay, thank you. So, any question? Any question? You remember the plane, if you remember that we have, what we have discussed in the first lecture, where you can map everything on a north pole, even the point and infinity, and that plane we call the extended complex plane. That includes infinity in it. If we have any value of z which is less than infinity, then it is an ordinary. Or to ordinary we call complex plane. Otherwise, you remember I have written one as a C plane and the other I have, I guess, written like this one. I don't remember exactly, but any notation you can use.
तो अगर कोई फंक्शन एनालिटिक नहीं है कॉम्प्लेक्स प्लेन में तो पॉसिबल है कि वो एक्सटेंडेड प्लेन के
एक ही होगा एक्सटेंडेड में, दैट इज f of z is equal to 1, कांस्टेंट फंक्शन. यही लुवेल थ्योरम है, यही आपको प्रूफ करना है घर जाके. अगर ना हुआ तो मैं कर दूंगा. Let me now prove something which is very important, you know. And you remember that now we have studied, if we have a complex function which is analytic, then if you remember in last lecture, Professor made a comment that you can expand a Taylor series around some point. The idea is the derivatives will definitely exist. And if the function is analytic, all its derivatives will be analytic too. But all we have to take care is the convergence of a series. So now I am going to talk in next 15 minutes about the convergence of a series, of course in a complex, for a complex numbers. The idea is exactly the same as that of the real numbers. And then I'll talk about the analytic continuation of a function. So you remember what is a Taylor series then? So I can write f of z as something where n goes from 0 to infinity, an, any coefficient, and z minus z naught to the power. I can take z naught to be 0, and then this is kind of an exponential series an if you have an is equal to 1 over n factorial. So this is kind of, instead of writing the exponential series, I can write any series and I can expand it around a point z naught where the derivative actually exists, df by dz at z is equal to z naught. And then you can write an. How you can calculate these coefficients? Okay, 1 over n factorial and then dn over dz to the power n, z minus z naught to the power n, z is equal to. Is it correct? It is correct. You can take it for one derivative and then you will see. You can get a1, a2, etc., etc. All right. So, if I have to decide this series is convergent or not, what is the quickest way to check? Every next term should be smaller than the previous term so that I can have the series to be convergent.
yes.
It means if this is less than 1, then I can say that the series is convergent. But there is a better way to check the convergence of a series. There are many tests that you can do. But you remember in the complex numbers, we have an exponential of iota, theta type things. Therefore, we can have kind of an oscillations, right? So instead, in order to remove these oscillations, the good way is to take an absolute singularities, absolute convergence test, where you can just do limit n goes to infinity, an plus 1 over an, right? The modulus of it, if it is less than 1, it is convergent. It means this term is smaller than this one for every value of z. If it is bigger than 1, then definitely it is not convergent. And if it is equal to 1, then it is an indeterminate. So these are the three conditions. And if you check this one, you can always find the radius of a convergence. And the radius of a convergence is just 1 over r we write. It is a customary to write 1 over r. You can write r and then you can revert these two. It's all up to you. So this is an plus 1 modulus over a. And you can see, even if involves any exponential of iota, theta type things, that is gone. That is why this is known as an absolute convergence. Now, for an exponential series, you know, an is 1 over n factorial. And by the way, you have to take n approaches to infinity. Now, what you can do is, then you can write an plus 1 is equal to 1 over n plus 1 factorial. Then you can write, this is for any z. So you can write 1 over r is equal to limit n approaches to infinity 1 over n plus 1, right? It's perfect because n is positive, because an plus 1 is 1 over n plus 1 factorial, the other is n factorial, so n factorial is gone, it is 1 over n. Now, if n approaches to infinity, this approaches to 0. It means r approaches to infinity. So, the radius of a convergence of an exponential series is infinite. You can make a circle as bigger as you like. It will remain convergent. Exactly. That is why you make a contour to be a small, to be a very big, to be a very, very big. Doesn't matter. And I'll prove that if something is analytic in a small region, then you can calculate in that region, and that is equal to the result in the bigger contour. This will prove in the last half of the lecture. So this is how you can, this is a technique that we use to calculate the radius of convergence for real functions as well as for the complex functions. There are many techniques. By the way, this is discussed in chapter in the chapter 5 of Arfken. You know, Arfken has discussed many ways for the convergence of a series, and this is one of them. And this is discussed in detail in chapter 5. So I have just used it as a tool to find the radius of convergence.
This is convergent all over the
Complex.
So what is it?
It doesn't matter if you calculate it. I'm saying that, okay, if exponential series is convergent in this region, you can say, okay, it is convergent in this region, it is convergent everywhere. Yes, exactly. And you will see, we'll prove it, that if something is analytic in this region, and if we can make something over here, and if we somehow make a connection between the two, the only thing is it has to be analytic in this region, and you can see this exponential has this ability because it is analytic everywhere. So whether I make small, big, big, big. So I'll come to this point.
So if it is convergent all over, does it mean that it is analytic?
Analytic, it's an entire function, exactly, it's analytic everywhere. It means its derivative will exist because an involves a derivative. Yeah, it has no singular point. And you will see if we have a singular point, then we have a problem. We run into a problem. We have to eliminate that singular point somehow. So, one very important thing which you can do at home even using your calculator, and that is, you have a concept of a geometric series, right? You know this z to the power n. Suppose you have a f of z is equal to z to the power n. It exists only when modulus of z is less than 1. That is why every next term will be smaller than the previous term. So this exists for if mod of z is less than 1. It means it converges for all the values where z is less than 1, but not where z is equal to 1. And how about this one, f of z is equal to 1 over 1 minus z. By the way, if you check it for a small value of z, these two will give you, sorry, I have to write sum over n, exactly, 0 to infinity. Thank you, sorry. Because this, for z smaller than 1, this is kind of a geometric series for this one. But the problem is this has a there is no condition that this exists only for z less than 1. This can exist for any value of z. If I just eliminate this condition that they have to match with z to the power n, then there is no condition on z. 1 over 1 minus z can be calculated for any value of z.
Sir, but z equals to 1.
But not z is equal to
1.
1. So the problem of convergence that I have over here, the problem of a convergence I have over here also. So it means if I draw a circle, I can say that, okay, around the origin, this is a point where the convergence is gone, where there is a singularity. Now you see, I can write this function in a very, very nice way also. You can write it as f of z is equal to 1 over, I can write this z as 3 by 2 minus z plus half. Why? 3 by 2 minus 1 by 2 is the same. Now if you expand the Taylor series, what you have? Let me take this 3 by 2 to be common from here. So I can write it as 2 by 3, 1 over 1 minus z plus half. If I take z plus half to be less than 1, I can expand the Taylor series. I can write the corresponding coefficients. How to do it? Any suggestions? Oh, sorry, नहीं ले सकता हूँ ना, ले सकता हूँ बिल्कुल. इधर भी 2 by 3 लिखना पड़ेगा. बिल्कुल, thank you, exactly. किसके लिए? No. This is z less than 1. There is no problem at all. Problem is when z is equal to 1 or greater than 1. For z is, that's why I said that if you take z less than 1, take a calculator, calculate the two, they will match point by point, but not value by value, but not for z equal to 1 or z greater than 1. So you see, what I have done is I have shifted this z. Previously, if I have something at z is equal to 0, now it is not at z is equal to 0, but it is at z is equal to minus half. Can you expand that, make the Taylor expansion of it? How we can make it? Any suggestions to make the Taylor expansions? This 2 by 3 is no problem. Is okay? It's fine. So now if you calculate the radius of a convergence for this, what will happen? What will happen if you calculate the radius of a convergence? 1 over r. What is the n plus 1 term? 2 by 3 to the power n plus 1. What is the nth term? 2 by 3 to the power n. So you can calculate 1 over r is equal to 2 by 3 to the power n plus 1 over 2 by 3 to the power n. So this is 2 by 3, or you can say that r is 3 by 2. So this series has a radius of a convergence equal to 3 by 2, but around, instead of a 0, now we have minus half. Right? But the problem is still at z is equal to 1, because we have written 1, we have manipulated 1 as 3 by 2, 1 by 2. So it means I can draw a circle that has a radius of 3 by 2, right? You can see that. You have a 3 by 2, you have minus 1 by 2 and 1. What is 3 by 2? But the problem is this point 1 is still a singular point. This, even you can write it as a 5 by 2, 3 by 2. Then you can move this point over here and you can make a bigger circle, but all these circles will match at this point. Even you can make it over here, but it has to match at z is equal to 1, anywhere you like. This way of writing the analyticity of a function is known as the analytic continuation of a function. This function is continued to be analytic at every point except where the series is not convergent. So this is the easiest way to learn the analytic continuation. Instead of you write z naught, z, etc., etc. This is the way.
You also need to go to the other side.
Yeah, exactly. You can also go, that's why I said you can go anywhere, but you have to touch this point, which is a singular point. That is why you can move on this complex plane anywhere. I hope that is an easy example.
I think it would be fun if you multiplied 1 minus z
Yeah.
with Go ahead.
Yeah.
1 minus z
Yes.
with 1 plus z plus
Okay.
z squared.
Exactly.
Plus-
Up to so on. Exactly.
Okay. Go ahead.
And then I can write this as a, because this is z to the power n then again.
Open it out. Open
Okay, all right. Okay, 1 minus z plus z into 1 minus z plus z square into 1 minus z.
I will
Okay.
write it as
Can
1
you-
plus z squared.
You can come. Let me erase it. Please.
So 1 minus
आ जाती.
this is
Oh, 1 and then you have to explain.
minus z
Yeah. Z
minus z squared
minus z
minus z cubed. And so this is always equal to
1. Exactly. Yeah, yeah. All right. Exactly. Thank you. Absolutely. This is you have done it in a very general way. So I can write it as a 5 by 2, 7 by 2, anything you can write. You still have a 1 that is equal to 1.
But there's a problem. There's a problem.
Convergence?
Can I-
You cannot go to that is equal to infinity.
Does this make sense?
Only for z less than 1
Or greater than?
or greater than 1. Yes. If you are not worried about the convergence of the series.
Because at z equal to 1, I am multiplying by 0.
0. Exactly. So can I move? So this is the way of you can check this analytic continuation of a function. So you can go home and try this for 5 by 2 and you can see that you have a circle which goes over it. Just a minor exercise, you know. And then you can generalize it for any m. How you can write m? Maybe you can write m plus something minus m minus something and then you have a radius which depends upon them that can generalize this whole stuff. So this is how we can make the analytic continuation for different values. So this is a good exercise. You know, these are small things that if you do, you will learn a lot because this mathematics is by practice only.
So इससे हम ये क्यों कर रहे हैं कि इसको इंक्लूड करने की कोशिश कर रहे हैं ना अपने इसका हम क्या करते हैं
नहीं include करने we are not going to include this point. We just want to उसके surrounding में exactly because our claim was that z to the power n was analytic function. It was an entire function. It is finite for every value of z less than infinity. What happens if I take the summation n is equal to 0 to infinity? I can make a series of it. Then I have to check it because is it an entire function? Is it a continued? Is a analytic function or not? So I have checked it.
एनालिटिक कंटिन्यूएशन
No, I'm saying that it is not necessary that you can just check 1 minus that. You can have any other this kind of a function. And you can always write, okay, if this is analytic over here, but our claim was that it is an entire function, it is analytic everywhere. So I have to check its analyticity everywhere except z is equal to 1. So I'm just wanted to join all the dots. An analytic function, entire function, and then a function which is entire everywhere, which is analytic everywhere, but not at a particular point.
सर उसको भी हम इंटायर फंक्शन ही बोलेंगे अगर वो एक पॉइंट पे
Nine. It has a singularity in it. Now, how we can remove the singularity? Next task, the removing of singularity.
ये जो आपने नया फंक्शन बनाया 3/2 वाली साइड पे इसकी फिर कन्वर्जेंस पुराने वाले से ज़्यादा है या फिर
जी बिल्कुल it has a convergence in this radius. Radius बढ़ गया क्योंकि we can always calculate the radius of convergence. That is analytic continuation. It is not convergent at this point, this point, this point, this point, this point. You can make it as bigger as you like.
सर बट इस केस में भी वो हमारे पास कन्वर्जेंट तो नहीं है ना z इक्वल्स टू 1
तो z is equal to 1 के तो एक ऐसा पॉइंट है जिसमें ये 1 over z इन्फिनिट हो जाता है. तो ये तो
सर
डिबेट एक ऐसा पॉइंट जो है इन्फिनिटी उसको खोल के हम क्या करेंगे
सर इसको
उसी
हम
point
इंटायर
पे.
फंक्शन नहीं कह सकते ना
सर सरफेस पे आ सकता है सिमिलर पॉइंट सर्कल के अंदर नहीं आना चाहिए.
Exactly. अगर अंदर आए तो हम रिमूव करेंगे अभी. अभी अंदर आए तो रिमूव करेंगे. And it is a deep connection with harmonic functions. You have del squared u, del squared v. Remember? They should be continuous. They are continuous, but not at this point. They are continuous at everywhere. So these kind of singular points we need to check for every function. Otherwise, this continuity is gone. Yes, please.
ये जो रेडियस ऑफ कन्वर्जेंस की बात कर रहे हैं, तो अगर स्मॉलर सर्कल जो है उसमें रेडियस ऑफ कन्वर्जेंस आपको पता है कौन से बाहर जाएंगे?
हाँ.
बेसिकली वो फंक्शन सिर्फ उसी सर्कल के अंदर आप डिफाइन कर रहे हैं.
जी.
लेकिन अगर आप शिफ्ट कर रहे हैं तो आप बाहर भी डिफाइन कर सकते हैं. तो एक डिफरेंट डोमेन के लिए आप डिफाइन कर रहे हैं जो एनालिटिक कंटिन्यूएशन क्या है कि एक फंक्शन सेम फंक्शन को आपने एक डिफरेंट डोमेन के लिए आप डिफाइन कर रहे हैं जो पहले उसमें नहीं थी. एनालिटिक कंटिन्यूएशन उस तरह हो गई. लेकिन जो सिंगुलैरिटी ऑफ कोर्स वो
रही है. अच्छा, सिंगुलैरिटीज पे हम सेपरेटली वी कम टू सिंगुलैरिटीज वेदर दीज आर एसेंशियल सिंगुलैरिटीज रिमूवेबल और नॉट रिमूवेबल. Whether these singularities are a simple like 1 over z or they are like 1 over z squared. How to check the order of a singularity or a pole? I'll discuss it in my next lecture. But for this lecture, the only thing that I need to check is this one. You just want to tell you that, okay, this is analytic everywhere over here. It is analytic everywhere over here. It will be analytic everywhere over here also, but not at this point.
Okay, sir.
Okay, good. Any other question, please? I guess enough about the differentiation. Now we have to come to the integration. And there is a very famous theorem, like we have Cauchy-Riemann conditions for the analytic function. From the differential Cauchy's Riemann conditions, we have these kind of a Cauchy's integral theorem, and there is a Morera's theorem that said that, okay, if this exists, then the function is continuous. I'll come to this theorem now. I'll prove the Cauchy's integration theorem, and then I will extract from that, because it is impossible to prove all the theorems. I don't know them how to prove so. It is not the time, it is the knowledge. So one last time, any question, please? So how you can integrate any function? Suppose I have a function, let's say in a complex plane. You can go from here to here. By the way, in a fancy language, call this as a contour. You can call it as a path, any path you can say. And that goes from, let's say, z naught to z naught prime, then this z naught prime, this zn. What you do is you can make a small steps, and then you can write a series S of n. How you can write it is, if I have a function, let's say I have a xi naught here, and I have z1, z2, up to so on, zn minus 1, because after that I have zn, and zn is z naught prime. So I am going from z naught to z naught prime. So how you can write it? In a discrete case.
Summation की case.
Summation over what? Yeah, exactly.
Summation over z.
Okay, summation over, you can say. So you can write it as summation upon n is equal to 1 to so on. Okay, I can write it. J is equal to 1 to n. Right? J is equal to 1 to n. F of xi j, zj minus zj minus 1. You can check it. You have written f of xi function over here. If you put j is equal to 1, it is between z minus 1 minus z naught. Similarly, you can write. And if I make these points closer and closer, what happens? It will become a continuous function. Okay, and then it becomes then I can write it as, for a very, very small steps, I can write it as f of, you can say z, and then I can write this as a dz.
Yes.
It's a function of z times dz. This is a standard way of integration from z naught to z prime. So, okay, z naught to z prime. By the way, this you can write for any function. Let's f is an analytic function. F is a function which is a u and v. And you remember that it is not necessary that I take this path, I can take this path, I can take any path in the complex plane. It means whenever I can take many paths, I can always write a parametric equation for the path.
Yes.
And in this way, you can integrate it using the parametric path. So you can write it as, it's not necessary to do it, but you can write it as f of z as u of xy plus iota v of xy. And you can go from any path from alpha, beta to anywhere you like. For example, you can go from alpha, beta, and this is your x, this is your y, and x is what real of z, y is what imaginary of z, and you can always write x, you can take a p as a p, x as a function of p, and y as a function of p. It means you can write df by dz, and you can express dx by dx and dy in terms of p also, and that's a parametric equation. Exactly, line integration, exactly. So you can always write it as, if you wanted to calculate df by dz, how you can calculate that? How you could, oh sorry, integration you have to do. How you can integrate that? How you can integrate along any contour, sorry. Still my mind is on the differentiation. This contour is not necessarily closed for the time being. How you can do it? You can write u plus iota v, and then you can dx plus iota dy. And then you can write it as, I can quickly do it because it is not necessary to do ux dx minus v dy. And then you can write it as, in the parametric form is u dx over dp, right? Iota. Oh, sorry. Let me do it again. There's no need to go very quickly then. So I can write it as, this is equal to c u dx minus v dy plus iota u dy plus v plus or minus plus dx. It is correct. You can always write dy by dx in a parameter dp. You can write dx by dp, dy by dp, dp. You can write it like this one. So in this way you can see that you can go on any path. But what will happen if the path is closed? What will happen if your path is closed? My claim is the following. My claim is, if you have f of z dz along any closed contour, it will be 0 only if it is an analytic function, it has no singularities inside this closed path. That is first condition. The path never crosses itself, you know. You can deform your path. For example, it's not necessary that you can write f of z and your contour is like this one. No, there is no problem. You can write any way. You can write this contour to be. Unless and until it is continuous, there is no problem. It has finite number of edges. There is no, it should be a closed contour. The whole idea is about this function. Function has no singularity. If the function has no singularity in it, then you can say that, okay, f of z dz is equal to 0. So we have to prove it. How we can prove it? Exactly. You remember you have seen these kind of integrals a lot in your mechanics and electricity magnetism. You said that whenever there is a conservative force, the potential depends upon the end points only. Exactly like this parametric equation, if you write dx in terms of a dp, then you can see that it depends upon the end points only. Right? So it means that if your path is closed, the famous example is the work done. You can say that work done is independent of the path followed, and if the work done is, we calculate for a conservative force along the closed path, then the work done is 0. So the conservative force, instead of a conservative force, we have an analytic function. Instead of a closed path, we have a closed contour with the condition that this has no edges in it. There's, exactly. So let me prove this thing now. So if you have any question, any suggestion, before proving it, you can just give it to me. No problem at all. I'll start from this thing which I have written over here, this one. But before that, you know, there is a very, very famous theorem which is known as a Green's theorem or Stokes theorem, right?
Yes.
You can call also Stokes theorem is the same, right? Okay. मैं कल के लिए करूँगा. So let me write then. Says that, okay, suppose you have a vector function in ordinary calculus. You can calculate a curl of that. So you can write let's say del cross V, and you know this is a vector, because curl is a vector, it means you have to multiply scalarly with an area on any curve. By the way, I always remember the dimensions, you know, kind of a, it's a naively way. Suppose it is a length, this has a dimension of 1 over length, this has a dimension of length squared. So if it means if I remove this del, I have to reduce one dimensions also. Instead of the area, I will go to the surface. So I can go to a closed path, which is V dot dl. Right? So this is closed path. I haven't written as a closed contour. Let me write this thing. Let me take area to be along z axis. It means only those components, V can be Vxi, Vyj, Vz, the vector calculus. It means the only component that will exist from this determinant is the z component, which is, I can write it as dVx, Vy by dx minus dVx over dy dx dy. This is the only, when I took area to be along z axis. I mean xy plane, z is the normal to that. So let me compare it with this one, with this way. Let me do it. So let me write in along a contour C, f of z dz over here also. So I can write it as C, and then I have u dx because I have to erase it, minus v dy plus iota, and then I have C u dy plus v dx. All right, now let me erase that side.
Left hand side. F of z dz, sir, नीचे last equation.
Oh, dz. Okay, so you see, now I wanted to make this as a closed contour. How I can do is I can, from this side I can go to this side, right? So you see, what is my u? If you compare this thing with this one, can I compare u and v then? अच्छा अच्छा ठीक है. How about this one then? Let me do it. Let me write a closed contour then. Okay, so there is one. Let me close it. This one. Now let me calculate this thing. U dx, as you said, minus v dy. Now I can compare, right? How you can write it? How you can write it? Sorry for that. This is closed contour. Sorry. Exactly. Because the function of this we wanted to calculate over a closed contour. So how to do it? Any suggestions? I have written something for you.
So partial v y by partial
Okay.
x into dy.
What is v? Two integrals, okay. Yes, yes.
So partial v y by partial x.
Minus partial v over partial x. Why? Because this has a negative sign. Vy, instead of a vy I have this v. And instead of vx I have u minus what is this, by the way? Can you tell me what is this?
partial v by partial y.
No, minus, okay, sorry, one is y. This one, right? Okay, sorry. Let me remove it. Let me put it over here because I'm too bad. This one. So, it's correct now?
Yes.
I'm not any problem. You can see this, instead of a vy, I have minus v. Instead of a vx, I have u. And then you have dx dy. Because if you integrate this one, you have dy with it. If you this one, you have dx with it. Exactly that thing. But you remember Cauchy's Riemann conditions of a function, because I said that f of z is an analytic function. So then you know that du by dy is equal to minus dv by dx. So it means this part is the first integral, which is u dx minus v dy. It is equal to on the area, and then I have du by dy minus du by dy dx dy, which is equal to 0. So the first part is 0. How about this one? U dy plus v dx. How you can write it? Just forget about iota, no problem, because we are just separating the two integrals, and then we add them by adding iota to it. So how you can do it? You have an area integral, that's why I write two integrals, and you can write dx dy, and then you have
u by x,
very good du by dx minus.
u by y, v by.
But this is a very nice Cauchy-Riemann condition in itself. Therefore, this is equal to 0. So you have seen that u and v are continuous, that their derivative exists. They lies in a closed contour. They are finite in that. The function has no singularity in that closed contour. It is analytic in that. And if it has no singularity in that, then this closed integral, this one is 0. So this implies that if you add the two, then you can prove that f of z dz is equal to 0. This is known as the Cauchy's integral theorem. This is known as Cauchy's integral theorem. So by the way, is it only for this one? Suppose I know the function. Now I'm making myself slightly more technical in that, because that is very simple. You know, this is a basic calculus theorem. Suppose you have a function that is analytic in one circle, closed contour, that is analytic, and you have a separate contour also, and that is analytic in between the two. It means it is analytic in the bigger contour also, right? So let me draw it and then explain it to you. That we will use to find something, the most interesting thing of today's lecture. You know, if we have singularities, then what will happen then? So let me first conclude this point. So if you have any question, by the way, sorry for. So what I have done is I have chosen f of z to be complex function, analytic function, applies the area theorem, Stokes theorem you can say, and then calculated the integral along a closed path and found that it is equal to 0, provided it has no singularity in it. So whenever we have a function with a singularity somewhere, and if we remove that portion from our contour, it means this integral is always equal to 0.
Yes.
And you see that we are moving towards the residue theorem. Right? That sometimes residue theorem is so important that sometimes we call it as a residue calculus also. So before moving, what I said is you have a function to be analytic in this plane, in this region, and you have a function to be analytic in between the two regions. Both are closed contours, no opening in them. The Cauchy's theorem says that, okay, f of z along the closed contour is 0. You can think of like this one. You can open this contour a little bit and this one a little bit, and you can join the two contours. What will happen? You have a new path. Suppose you are going from in this way, right? You come to this side, this way, this way, this way, and this way. So you have only one path. Suppose this is your C1, this is your C, and now you have a new path which is, let's call this as C prime. Now you have a new path which is C1. It means your integral on this, because it has no singularity in it anywhere, so my point is the C1 f of z dz is equal to 0. And you see what Hassan said in his comment, you will see from the integral theorem now. Now if you bring these 2 points closer and closer to each other, then they will join, this will join. It means that I have an integral which is inside, I have an integral which is outside, we have two contours, and both, sum of both is equal to 0. Right? So this path you can always close it like along a C, f of z dz, this one is on C, and then you have other is C prime. This curve become like this one then. If this is this one, this is this way. One is clockwise, other is anti-clockwise. So you can write it as, so it means you maybe you will see some books where they write like this one, that this is anti-clockwise and this is, they put a sign of contour on this closed curve. Otherwise you have to write anti-clockwise and clockwise, etc., etc. So if some function is analytic in this closed contour, its answer is the same as I calculated in the bigger contour.
सर वहाँ पे एक क्लॉकवाइज और एक एंटी क्लॉकवाइज होना जरूरी है?
बन यही रहा है ना, जिस तरफ से आप शुरू करेंगे ये उलट ही चल पड़ेगा उससे, और कोई ऑप्शन ही नहीं है आपके पास.
सर ये तो तब है जब हमने वहाँ से एक पॉइंट पर मूव करके उनको ज्वाइन किया है ना,
तभी तो सम ऑफ 2 इज इक्वल टू 0 होगा ना. अदरवाइज कैसे करेंगे हम? एक इसका साइन फिक्स करेंगे 2 पाई आयोटा और माइनस 2 पाई आयोटा, डोंट वरी, हम इसका फिक्स करेंगे अब साइन. लेकिन इट्स प्योरली अ कन्वेंशन. यू कैन चूज एंटी क्लॉकवाइज विद वन साइन एंड देन यू हैव अ क्लॉकवाइज विद द अदर साइन एंड वाइस वर्सा. But you have to be consistent with your choice throughout your calculation. So this is, by the way, the Cauchy.
The direction of increasing theta.
Exactly. Direction, absolutely. That is very correct. Absolutely, yes. Direction of increasing theta, yes. Because now we have 2 pi iota downstairs. Then I'll explain that. Absolutely. Thank you. So any question? The punchline is analytic function. If it has no singularity in a closed path, integral over the dz is always equal to 0. So in this way you can find anything that is the coefficient that are involved in the function. Now let me prove one very, very important theorem, which is the Cauchy's integral formula. And then I'll come to Taylor series, which I have already talked, Taylor sum, and then I'll come to one another series where n has a negative, z to the power n with n to be negative powers. Then it has a singularities, and then I will basically, you can say that combine the two, one integral theorem for these kind of functions, and then you can do these kind of integrations in Fourier, and you can improper integrals that involve sine theta, exponential, etc., etc. So now before that, let me prove one very important thing. Suppose f of z is an analytic function on some simple contours. When I say simple, it is kind of all these conditions that were satisfied, no wedges, no crossing, etc., etc. So then you can write integral f of z, suppose over z minus z naught dz. My f of z is basically, my f of z is analytic function. But the problem is that this is not analytic. This is analytic everywhere, but not at z is equal to z naught. By the way, if you integrate it on a z, what you will get? From basic calculus. The idea is this one. You have to prove that f of z naught is equal to 1 over 2 pi iota on a closed contour. You have to prove this one. This is the very, very famous Cauchy's integral formula, and from this we can see the residue theorem also. The only thing that you remember is, if f of z is an analytic function, then its integral in a closed contour is always equal to 0. No, my f of z is analytic. How about let's define f1 of z to understand this better, which is equal to f of z over z minus z naught. This is analytic, by the way. F1 is also analytic, except z is equal to z naught. Right? So this implies is f of z, f1 of z has a singularity. You can call it as a singularity, you can call it as a pole, whatever you like, the name you like. We usually call in complex variable these as poles, at z is equal to z naught. And if you read these integrals in a lively way, what you see? You say that, okay, you calculate this integral, the answer will be the value of this function at a singular point.
Yes.
Right? Yes. Along with this 2 pi iota.
Because elsewhere it's analytic.
Huh? This is what Professor said, that you have an increasing theta, you have a 2 pi over here. So if you start from 0, you will go to 2 pi. Let me prove this theorem, But before that, if you have any questions, so please, you can ask. Okay, so exactly the same knowledge that we have used recently. Now I have a point z naught, and let me draw a small contour C prime around z naught. And I can make a bigger contour, which is C, that contains z naught. My function is f of z is continuous everywhere, but f of z is analytic everywhere in this range, but not over at this point. That's why actually my problem is I have drawn it at a very, very small contour, you can say, around this z naught only. So how to do this integral?
Sir?
Let me remove this singularity from my integration. Yes, please.
सर जो पहले हमने किया था उसमें जो वो सिंगुलैरिटी थी वो हमने बाउंड्री पे ली थी, सरफेस पे.
नहीं, वो फंक्शन ऐसा था. अगर उसके लिए मैं कंटूर बनाता, ये पॉइंट था ना.
यस.
तो मैं इसके घेर छोटा सा सर्कल बनाता और एक और बड़ा कंटूर बना देता, कोई मसला नहीं था.
ओके.
एंड आप देखिएगा मैं इसी को ज्वाइन करूंगा. जब मैं कैलकुलेट करूंगा तो देन यू विल रियलाइज दैट इट इज एप्लीकेबल एवरीवेयर.
दो सर्कल है, एक सर्कल उस सिंगुलैरिटी के अराउंड है और एक फंक्शन का सर्कल.
बिल्कुल, एग्जैक्टली. Because you see these are two different functions. One is f of z. F of z has no problem with this z naught. Other is f1 of z. That is analytic in between the two curves. It is analytic everywhere. And you will see that I'll bring this z, c prime smaller and bring it to z naught. That is why the value of the function is z naught. I have drawn it a bigger size just to distinguish you that, okay, I have two circles. Okay, right? So for this one I'll come to, once I prove it, then I'll come to this point. Okay. Right? I'll show you. Path. It is a, अगर इसी की सीरीज खोल के आप करेंगे तो वहीं से रेडियस निकल आएगा. This is a closed contour. Closed contour has any radius in it.
This is a path we drawing ourselves or go actual radius.
Exactly, वो तो एक particular problem के लिए था ना. This is a generic function. This is a very generic function. What is z naught? What is, if I define z naught to be 1, let's suppose, then I can write it as a minus f of z over 1 minus z. Then it again has a pole at 1 minus z. Z is equal to 1.
So एक just confusion है. ये जो theorem था इसमें ये था कि boundary पे अगर pole हो या
कहीं singularity ना हो.
सर एक बाउंड्री का भी था वो पता नहीं इसमें आता है या फिर जीरो वाले में आता है.
पहले कर लें फिर देख लेते हैं कहाँ पे आता है. सब कुछ यहाँ से क्लियर हो जाएगा. ऐसे वो लेट मी प्रूव दिस थ्योरम एंड देन विल सी. इसकी एप्लीकेशन करेंगे सब कुछ क्लियर हो जाएगा. ना हुआ तो उम्मीद करिए कौन सा भाग रहे. ओके, सो लेट मी draw this figure again and explain it to you before calculation, because calculation is not difficult. So this is x, and remember when I say x it is real of z, and when I say y it is real of imaginary of z. I said this is my point z naught, and I have a contour over here, and I have a bigger contour over here. This is C prime, this is C. Now what I'll do is the following. Once again, I will cut the two paths. Let me see if I have some colored chalks also. So you can see that you can join this with smoothly this one, and join this with this one. Where is your singularity now in this new path? Let's call this as a path C1. There is no singularity in this path because you have deformed your contour. This is known as a deformation of the contours in such a way that you have removed this singular point from your path. What will be the answer by the Cauchy's integral theorem then? Exactly, not on any other path but on f1 of z dz is equal to 0 because no f1 has no singularity. Now let's calculate and see what will happen. You see, let me draw this over here, this way, at least 3 arrows. This will come in this side, this will go to this side. Let me write this as 1, 2, and then I will write it as 3 and 4. These are 4 points. So you can see that I can move along two paths. I can move from 1 to 3 along C, from 2 to 4 or 4 to 2 depending upon the direction, because if I write the direction, you can see this, then I can move from 4 to 2 along C prime, and then I move from 2 to 1 and then 3 to 4. So this C1 path has 4 contributions. Contributions from C path C, contribution from path C prime, contribution from these two arms of my deformed contour. So can you write this now? Please guide me how to write it. कहीं से भी शुरू करो. Let's start from this. Okay, so you can write it as from 2 to 1 f1 of z dz plus 1 to 3 along C, f1 of z dz plus, then you have
4 to 3.
Okay, so we have 1 to 2. Oh, sorry, is it wrong, right? Is correct? Or 2 to 1, right? Okay. 2 to 1 and then 1 to 3 and then
3 to 4.
3 to 4, f1 of z dz, and then you have 4 to 2, but this is along C prime f1 of z. So you see, how you can say that this is smooth? This is smooth joining. How you can say that? Because the final point of previous integral will act as an initial point of the point. So it means the contribution of this end point over here will cancel with this, right? And similarly, of the 4 will cancel with this one, and we have perfectly fine this C. This integral is basically, this one is my integral over C1 f1 of z. Is correct? But this
हर पाथ के लिए सेम ही रहेगा.
function तो same है ना. Function is f1.
लेकिन उसका पाथ का स्ट्रक्चर तो
Structure doesn't matter.
अलग-अलग है.
Structure doesn't matter. Function is function. I said function f1 lies in this everywhere, except at z is equal to z naught. So what I have done is I have just pulled out z is equal to z naught. I have just abolished that apart from this one. So ऐसे ना बिल्कुल निकाल के बाहर फेंक दिए.
Z is equal to
Z naught.
not included.
Exactly. Not included because we have contoured out this one. Cut out this time. This is also known as cut out. Because Cauchy's integral theorem is for any closed path where the function is analytic. And in that closed path, the integral is always equal to 0. Now, you can bring these two. What will happen? If you bring them closer and closer, you have this line over here, this, and these two lines become one line. So it is like one line where one integral is going on this side and other integral is going on this side, and their contribution will exactly cancel each other. So it means this one and this one will be cancelled. And what you have now? You have an integral along C and integral along C prime. So you can see that, okay, you have let me write it slightly bigger. You have anti-clockwise, this is anti-clockwise, right? Let me put the direction of contour over here also. And you can write f1 of z dz plus, this is my clockwise, f1 of z dz is equal to 0. This is along C, this is along
C prime.
C prime. Now if you take the on this side, then I can write then I can write this one. This thing is equal to minus of integral on this side. This is C prime and this is C. By the way, clockwise is and anti-clockwise in my customs, they have opposite sign. So it means I can also write it as in the anti-clockwise. By the way, you have proven a very, very important theorem. If you calculate your integral in a small region around the singularity, then you know it everywhere. This is very, very important theorem. This is the very, very important consequences. So, but remember, it means if you know it everywhere, you can define the derivatives also.
Yes.
If I can calculate the integral for this one, f of z over z minus z naught, I can calculate the integral for maybe z minus z naught to the power n also. And how I can relate it with the differential, this you will see. But this is fine, right? You remember in the first lecture, the comments Professor made that if you know this in a small region around z is equal to z naught, then you can calculate it everywhere. Yes. This is exactly the proof of that. So this is my main thing for this today's lecture. And remember what I said, C prime is very, very small. So let me make it actually small. That's it. But before that, if you have any question, please feel free to ask. We deformed the contour. पहले हमने एक पैरामीटर लिया ना, पैरामीटर की कोई इनसे पता नहीं चला था. अब हमने, but you can just understand the main point. You know it in a small circle around that singularity, and that the answer is equal to anywhere outside that small circle also. But the path should be closed, and you will see. Just a moment. And this is my anti-clockwise convention, right? Let me take C prime to be really small. So let C prime is a very small circle around Z naught. So I can write Z as a function of theta, and this is what Professor said, that it is increasing theta, I'll write. So I can write it as Z naught plus A e to the power iota theta. So that my Z minus Z naught becomes A e to the power iota theta, where A is the radius of the circle, small c prime, that I have drawn around Z naught. Now you have to calculate this thing, you have to see this factor of 2 pi if you have or not. So let me write integral C prime. By the way, if you remove direction from this point, then you have to remove the direction from this point. So if it holds for clockwise, it will hold for anti-clockwise. So it doesn't matter you start moving in this direction. You can also start moving in this direction. The two sides will be equal always. Right? It's my customary that I have chosen this direction, like a left instead of a right. So now, what is my f1 of z? Z is a function of theta, and dz and z is a function of theta. How you can calculate this one? First you can calculate dz, which is equal to a e to the power iota theta d theta along with iota.
Yes.
Right? And then you can write it as c prime f1 z, which is a function of theta, iota a e to the power iota theta. कुछ गलत तो नहीं किया? किया तो बता दें।
थीटा भी आएगा ना साथ में।
जी?
डी थीटा भी लिखिए। डी थीटा भी सर साथ।
डी थीटा भी आएगा, बिल्कुल ठीक है। You remember what is f1 of z? Because we know only f of z, which is analytic, not f1 of z. So it means that you can write, but you have f1 of z, which is a function of theta, is equal to f of z, which is a function of theta, has no problem at all over z minus. And you remember z minus z naught was what? And then you have f of z, which is a function of theta, over z minus z naught is a e to the power iota theta. It means I have this integral over c prime, which is f z, which is a function of theta, over a e to the power iota theta. But I have to make one change now. Instead of writing c prime, I know that if I have a closed path, I start from 0, then I can make a whole path if I join it at the other end, which becomes then 2 pi. So it means instead of c prime, then if I make an angular integral, I can write it as 0 to 2 pi. So you can see that I have at an increasing theta. So if you increase theta from counterclockwise, if you increase from this way, it all depends upon your convention. Whatever you choose, you have to be consistent with that. And then you have iota a e to the power iota theta, and then I have d theta. So a is gone, this is gone. So this becomes 0 to 2 pi iota f of z, which is a function of theta, d theta. Now let me make this circle to be very, very small. This means that for a approaches to 0, z approaches to, z of theta approaches to z naught. But z naught is constant. So it means I have iota f of z naught and then 0 to 2 pi d theta, which is equal to 2 pi iota f of. You can say you have proven it in a very elegant way. Nishad, this is the answer to your question. You know, in a small circle, and there you have only 0 to 2 pi. So the factor of this singularity point was just this 2 pi. And then what you have to do is you have to put z is equal to z naught. But remember, it doesn't matter whatever path I have. If that point doesn't lie in that path, the singular point, answer is always equal to 0. So sometimes we give you a question from -5 to 5 and write something x plus x minus 10 downstairs. -5 to 5 have no x is equal to 10. Answer is 0 instead of calculating everything, So all you have to do is your singular point should lie in the path, inside the path. So you can see that f of z naught, so this implies f of z naught is 1 over 2 pi iota integral over c and then f of z over z minus z naught c prime dz. Perfect. You see I have this 2 pi iota divided by this one. But this, there is nothing special about c prime. This holds for every c that is bigger than this one. So it means I can just write it as equally good as Instead of removing it, I can write it as 1 over 2 pi iota integral over C, and I always choose this anti-clockwise convention somehow. F of z dz over z minus z naught. Fine? Any question? So this is the proof of the residues theorem. This Cauchy's integral formula or the residue theorem. The answer is 2 pi fz if that point lies. But you see, I have only z minus z naught. Every time I have this kind of a pole which is linear, this is known as, इससे सादा क्या हो सकता है? If has a singularity of power minus 1, that is the simple pole. The coefficient of that simple 1 over z is the coefficient of that 1 over z is the residue. I'll prove it also. So if you have any question, please feel free to ask. Or anything you want to correct, that is most welcome.
सर 0 से 5 तक इंटीग्रल है और 5 के ऊपर ही सिंगुलरिटी है बाउंड्री के ऊपर, तो वो 0 होगा उसका इंटीग्रल या फिर उसका इंटीग्रल 0 होगा या फिर 2 पाई आयोटा
2 पाई at z is equal to 5 आप उसको कैलकुलेट कर रहे हैं ना?
बाउंड्री के ऊपर.
Okay. Answer is infinite then. Why your contour is including z is equal to 5? You have to make a path which is beyond that path. That is equal to 5. Close karna you have to. This is not a closed path. You know there are 3 conditions. F of the function should be analytic. Path should be closed. It has no knots in it. And the third thing is these two are finite edges. Right. This is your open path then. And you will see these kind of open paths will define kind of a cut over there, and we'll do it. These kind of things, branch cut and branch points, etc.
सर इस चीज को हम जनरलाइज कर सकते हैं लाइक
Let me do it.
z नॉट की होल पावर n.
Exactly. I can do it. Absolutely, you are very right. That is very, very good question. That if it holds for z minus z naught, can we say that this will hold for any part of z? Exactly. And for that you have to take z as a parameter and then differentiate your function with respect to z naught. Then what will be the answer? If I write it like this one. So d by dz naught of f of z naught. I have 1 over 2 pi iota d by, let me write as a closed contour C, and then over here f of z over z by z naught dz. By the way, it has no z naught.
Yes.
Right? What you will do is, this is a total integral. If you bring it inside, it becomes a partial integral. And then answer will be what? Answer will be 1 over 2 pi iota closed path f of z over, if you differentiate it with respect to z naught, then you have z minus z naught squared, and then you have minus 1 to the 4. And why I have written minus 1 squared? Because one comes from the power and the other comes from z naught.
Yes.
So this becomes 1 over 2 pi iota, and then I have on a closed path C f of z over z minus z naught squared dz. Right? How about this is, so you see, with one differential I have one extra power.
Yes.
With two differentials I will have two extra powers.
Yes.
With three differentials I will have three, but upstairs I have factor of 1, 2, 3, 4, 5 up to so on and so forth. So in general, you can write dn over dz naught to the power n, f of z naught is 1 over 2 pi iota f of z over z minus z naught to the power n, and then I have to multiply by n factorial, I guess. N plus 1, exactly. Exactly, n plus 1 is fine now, n factorial. The order of derivatives will come over here. Amazing. If you have a function which exists at z is equal to z naught, all its derivative will also exist. So if you have a f of z naught to be analytic, all its derivatives are analytic. This is an amazing property. So this is the general formula, right? So by the way, this is important formula. Why I'm saying it's important? If I have a z squared type, I can make a calculation for simple pole and then take a differential.
Yes.
Answer will be the same instead of calculating this z squared. Any question? Exactly. Now you can open the Taylor series exactly for all parts. Absolutely. For any function around z is equal to z naught. You have already opened it for the differential.
Yes.
But the idea is z naught was a point where this function f1 of z was singular.
Yes.
But now you have a value of a function fz at that z is equal to z naught. And then you can calculate the differential. It's continuous now. It's perfectly fine. Okay, so what I am going to talk about in the second, in next lecture, let me quickly say one thing in next few minutes and then I'll close at this point. So that you know, you remember a very, very simple function f of z is equal to sine z over z. For real function, we learned L'Hopital rule and we say that, okay, differentiate upstairs and downstairs. And then if z goes to 0, the answer is 1. And this function has a problem. If z is equal to 0, this is infinite. But z approaches to 0, it is 1. And for any other value of z, it is sine of z over z. So it has a kind of a very strange behavior that as z approaches to 0, it approaches to 1. And for any value of z other than z approaches to 1, it is sine z over z. If you open the series of a sine z, what will be the series then? Okay, so let me write it like this one. So you can write it as z minus z cube over 3 factorial plus over z. You can divide it that. You have 1 minus z square over 3 factorial plus up to so on and so forth. There is no problem at all. Now if you put z is equal to 0, z goes to 0, this answer is 1. No problem. For a very, very small z you have written. And now if you put z is equal to 0, the answer is 1. What will happen if you have this kind of a function? Instead of a f of z, I have sine of a z over z squared. Then what? Then situation is different then. Then I have 1 over z minus z over 3 factorial plus up to so on. You can see that now if I have z equal to 0, the answer is infinite.
Yes.
But this z, 1 over z is a simple pole. In this series, in this function, you have a singularity at z is equal to 0, but that is a simple pole, it is 1 over z. And for the simple pole, we know how to do calculation using the residue theorems. I'll solve this integral. And why not I make my series like this one? You remember we have written f of z is equal to an z minus z to the power n from n is equal to 0 to infinite. You remember?
Yes.
Instead of 0, if I write it from minus infinite to infinite, then what I have? A to the power, a minus, let's say minus 1, you can say. So you can start, let's minus 1. Let's be very simple. Then you have a minus 1, z minus z naught to the power minus 1.
Yes.
Then you have a constant term and then you have a z. These are all fine. The terms which are proportional to z, they have no problem at all with the singularity because they will vanish once you go to the singularity point. These kind of series that involve, that you can translate from 0 to infinity to, from minus infinite to infinite, part of it is non-singular, part of it is a singular. These kind of series are known as Laurent series. Laurent series, they call it as like this one. So in next lecture, I'll talk about the Laurent series, its relation with the residue theorem, how we can calculate the residues for different things, and then I'll give you the assignment for the Riemann zeta functions calculation, because one has to do this calculation of the Riemann zeta function. Say z is equal to zeta 2, and then you can calculate zeta 4 up to so on and so forth. One has to do it once in a life. कौन सी चीज? Exactly, then you have a green. Okay, so you know these kind of things we always encounter 1 over z type. Suppose z is e minus e naught, then this is kind of a propagator, and then it becomes e square minus e naught squared. It becomes a relativistic propagator. So instead of a one pole, it has two pole. How we can do the residue theorem, how we can remove the singularities, this we'll discuss in this course, definitely. Absolutely, this has a relation even in fluid mechanics, condensed matter, in particle physics, etc., even quantum mechanics also. So we'll discuss this Green's functions calculation. So let me summarize everything what I have done in 1 minute. We have started with the analytic function. We said that if it is analytic for every value of z less than infinity, it is an entire function. And if it is analytic at z for the extended complex plane, which includes infinity, then the only possibility of the function is the constant function. It is a Liouville theorem. And this you can prove from this A and, okay, so next lecture we'll do it. I'll tell you how to do it. And then we have studied Cauchy's integral theorem. We said that if function is analytic in a closed contour, it has no singularity, then integral along the closed path is always equal to 0. And by the virtue of that, what we have done is, if we have a singular point, but that singular point is a simple pole, like 1 over z, and the f of z, which is upstairs, was analytic, then we can also calculate f at z naught and all its derivatives by using this residue theorem. Next lecture, I'll apply it. First, I'll like Taylor and Laurent series, and then Laurent series, and then I'll calculate the residues, order of a pole, how we can calculate the order of a pole, etc. This will be the content for the next lecture. So thank you very much.
Thank you.
One small.
Yes, please.
Your starting point was Stokes theorem.
Exactly.
All these wonderful results come from
Absolutely.
Yes.
then you get integral around the
Close.
curve is equal to 0 for the analytic functions. I'm doing a little bit of self-advertising, but this is